Stripping down science. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Kat Arney. Hi, Kat.
Hello.
Now, on this week's show, we'll be finding out how a laser is helping scientists to kill just bugs and viruses, but without harming human cells, and they think that might help them to sterilise donated blood products like blood transfusions. Also, the nano radio. Scientists have made the world's smallest radio receiver. It's the size of a carbon nanotube, and that means it's less than 1/100th of the diameter of a human hair. And also, how a flower, which is growing high up in the Alps, could hold the key to a new way to make better sun creams. That's all on the way.
Also this week, we are in search of the Garden of Eden. We're going to be talking about where did we come from. We've got Professor Chris Turney coming on the show. He's the only man who can claim to have dated a hobbit. Not in the romantic sense, though, unfortunately. He'll be talking about the origins of modern humans and where we came from. We're also going to be getting to the bottom of how the English Channel formed and cut us off from those pesky French. And Jenny Collier's here to tell us how it all happened. And for those of you with a fire fetish, we're going to be hearing the evidence for man's first use of fire. And it's actually a lot further back in time than you might think.
Thank you, Kat. Plus, we'll be hearing from the two guys who broke the record for the world's highest paragliding flight. They actually flew over Mount Everest, and that's 30,000 feet.
When you think about it, 30,000 feet is the height of an aircraft flying. So when you go on your holidays and you're flying at that type of feet, you imagine looking out of the window and seeing a guy in a parachute basically flying past you. It's quite a challenge.
Absolute nutter. So we will be catching up with the high flyer Bear Grylls and his team later on. So if you've got any questions about the origins of humans, where we came from, have we got there yet, and how we came to colonise the world, or if you'd just like to say hello, email chris@thenakedscientists.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's kick off with a look at what's been happening in the news this week and some of this week's top science news stories. Very exciting piece of research which has come out of the University of Arizona. This is Professor Sen and his colleagues, and what they've managed to do is come up with a way of using laser light to kill just bacteria and viruses, but without harming human cells. And they think this could be very useful for doing things like cleaning up human blood products, because when someone has a blood transfusion, these days we do try and screen for various viruses that might be in there. But if we don't know about a certain virus because it hasn't been discovered yet, doesn't mean it's not there, and it could be being transmitted. So it would be better to do something to make sure that all transfusions are as safe as they can be. What they do is to blast the sample with very, very short femtoseconds, that's billionths of a millionth of a second long pulses of light from a laser, which is working in what's called the near infrared. So it's just slightly off the end of the visible spectrum of light, at the red end of the spectrum. And what they find is that when you do this with viruses like bacteriophages, which attack bacteria, and also bacteria themselves, they seem to be vulnerable to the effects, and they all die after they've been blasted in a solution for about an hour. But human cells, when they do the experiment, aren't harmed, and they don't know exactly why, but they suspect it's got something to do with resonance. Now, what I mean by that is that in the same way, Kat, as if you take a glass and you play music at it at a certain frequency, if it's a very high purity glass, it's possible to shatter the glass. And they think that the laser pulses which hit proteins in the coat of the microbes make them shake at just the right rate, that it then tears jagged holes in the coat of the microbes, either the viruses or bacteria. But because the human cells are much bigger, they're not vulnerable, they can take much more damage, and it doesn't seem to do the same thing, so it leaves them unharmed.
Well, that could be really quite useful. Let's see if they get that working. And anyway, I'm going to tell you now about the nano radio. I think this story is so cool, because never mind the nano iPod, a team of researchers at the University of California at Berkeley have built a working radio made from a single carbon nanotube. I mean, that's a pretty small thing to take jogging. But you fix the tube between two electrodes and it can fulfil all the functions of a radio. It acts as an antenna, a tuner, an amplifier, and a demodulator. That's the bit of a radio that kind of decodes the radio signals. And the team showed that their nano radio could tune into a radio signal that they generated in the room and play it back through a speaker. And rather cheesily, the first song that they broadcast on nano radio was Layla by Derek and the Dominoes, but then they followed it by Good Vibrations from the Beach Boys.
How do you tune it in?
Well, it works. You have the nanotube fixed between two electrodes. When a radio wave passes across it, it causes a change in the electrons that stream through the tube, and it causes the tube to vibrate. And this acts as the radio. It decodes the signal, transmits the information. If you lengthen or shorten the tube, you can control the frequency that it'll respond to, because obviously it's got a different resonant length. And using this technique, the researchers, they could make it work across the frequencies that you use for commercial radio stations.
That's all very nice, but most people have got bigger ears than that.
Yes.
So why is this useful?
And it's not just a gimmick. And one of the great ideas is that you could actually use it to radio control nano-sized devices. So if we get to the point where we can have sort of nanobots in your bloodstream doing jobs, clearing out your arteries or something, you could have radio control for these things at a distance. So that would be a really nice idea.
I look forward to seeing that emerge, hopefully not too long into the future. Now, talking about things that are very small, out of sight and out of mind doesn't mean out of danger, because there's a very interesting study which has been published this week by Emma Tutin and her colleagues. They're from the University of Plymouth, and they've been wondering about a problem which people have been worried about but never had any proof for quite some time. And that is that when we put plastic into the sea, the big lumps of plastic that we make, like nylon and other perspexes and things, eventually get ground up and they make very tiny pieces of plastic called microplastics. And most people just thought, well, they just eventually disappear. But they hang around for a very long time. And there's one very important point, is that because they're made of oil, these things attract other chemicals in seawater which are oily. That includes things like PCBs and other chemicals that are oil-based,
bad stuff,
which can be what are called persistent organic pollutants. They're things which can get into your body and build up, like DDT. Now, these things are normally in the ocean in very low concentrations, these chemicals. But when you add these little bits of plastic, which happens naturally because the plastic breaks up over time, the oil-based chemicals glue on to the plastic because they like the fact that it's made of oil. And so the plastic becomes enriched with this cargo of toxic chemicals. It then sinks to the bottom. And normally it would just be buried, but of course there are animals down there. There are lugworms and there are also other molluscs and things that are filter feeders. They churn through the sediment and they take into their bodies these tiny plastic fragments. Now the plastic doesn't harm them, but the chemical cargo gluing to the plastic does, because it now dissolves in the bodies of these worms and other animals. It then enters the food chain because bigger animals come along. They eat the worms and things, and this concentrates these chemicals up the food chain. And because we're in the habit of eating these things, including things like crabs, it ends up in us. And so these chemicals which we're saying, well, the water's at very low concentrations, it may actually be a bit of a worry. And these guys have done experiments now where they went to various places around the UK and got lugworms, which fishermen use as bait, actually, but they're a convenient way to study the problem. They got some sediment. They set these tanks up in their laboratory and they added some of these organic pollutants to the tank. And they also added to some of the tanks tiny fragments of plastic. And then they measured how much of the chemical got into the worm. And in the tanks where the plastic was present, 80% more of the chemical went into the worm's body. And so we're at the level where you're seeing these things in the sea at levels where this really could begin to happen. So it's bad news for the food chain.
It certainly is. I wonder if there's any way we can try and get the plastics back out of the sea or just stop throwing them in.
Once they've got to these microplastic ground up tiny particles, they're too small to see. There's no way we can really get to them. The only thing we can hope for is that we can stop putting more plastic into the ocean and try and stop it happening in the first place.
Nasty.
But it's certainly worrying.
Yeah. Anyway, a totally different story now, because researchers at the Case Western Reserve University in Ohio have managed to breed some mighty mice. I think these are fantastic. They're mice that are capable of running at a top mousy speed on a treadmill for about 6 hours without stopping, and this makes them sort of superheroes of the mouse world. And the impressive little beasties have been genetically engineered to have unusually high levels of an enzyme called PEP-CKC in their muscles. And this enzyme's normally involved in glucose metabolism. It helps us to make energy from things like glycogen and fat in the body, so not just the sugar you take in your diet. Now, the researchers found that these mice, they eat 60% more than usual, but they stay fitter, slimmer, they live longer, and they breed for a longer length of time.
It's like Metro Mouse.
Well, yeah, they're cool mice. They're normal mice, and they tested them on treadmills, and the scientists found that the ones who'd been modified could run for nearly twice as long as unmodified mice and at much higher speeds. And the lead researcher that has actually compared them to someone like Lance Armstrong biking up the Pyrenees, because he points out that the mice use mainly fat rather than sugar for making energy. And this means that they produce very little lactic acid. Now, it's lactic acid that builds up, for example, in our muscles when we exercise, and that causes pains and cramps and limits how much exercise you can do. Now, unfortunately, as well as being, more active and virile, these mice are actually a bit more aggressive, so it's not all good.
Is that the downside then? Because one wonders, if this is so good, Kat, why doesn't every animal have this particular gene in this particular way? Because it sounds really good.
We all have it, but they've been designed to sort of specifically overexpress this gene in their muscles. So probably in normal life, we're all using this enzyme a bit to make make energy when we need to, but they've kind of souped it up in these mice. Because we have so much sugar normally in our diets, I guess there's not much need for it.
So what is this kind of proving to researchers?
Well, it's part of an ongoing research project which is aiming at trying to understand the roles of these enzymes in muscles and fat tissue. And, who knows, maybe we could breed mighty humans in the future, but I think that's probably a long way off.
Certainly sounds like it could make the Olympics a very interesting event, although quite boring to watch because you'd be waiting for years for people to finish. You'd have to have races that were sort of the 5,000 kilometres or something.
The GM Olympics.
We're talking about nature being a funny thing. Just to round off, scientists have been up the Alps this week. It's wonderful to do research in nice places, isn't it? And they were intrigued by Edelweiss. Now, this isn't just a tune in The Sound of Music. It's actually a plant. And it grows high up in the Alps, and that means it's exposed to big doses of ultraviolet because it's at high altitude. So if it's getting big doses of ultraviolet, how does it protect itself? Why doesn't it get damaged by the ultraviolet? And that's what Jean-Paul Vigneron and his colleagues wanted to know. They're a research group based in Brussels, and quite appropriate they're in Brussels, being as it's a plant. But they studied these Edelweiss plants, and they thought, well, if it's not susceptible to UV, perhaps it's got some clever way of reflecting all the UV back off the plant. So they looked at the plant with a camera that can pick up what colours of light are being reflected, and they were really shocked to see that all the UV light that was hitting the plant was being soaked up. So it's absorbing the UV, not reflecting it. That's really strange.
Where does it go?
Well, that's what they wondered. And if you look at the plants, it's really characteristic because the leaves are really hairy. They're covered in this fine, white, downy fluff. So they thought maybe the hairs hold the key. So they put them under an electron microscope, and they found the individual hairs are themselves made of tiny fibres. And the tiny fibres are 176 nanometres. Now, the reason I'm giving you that gratuitous detail is because that's almost the same wavelength as ultraviolet light. So when the ultraviolet light comes waving in from the atmosphere, it hits these tiny fibres, they can interact with it, and they actually soak up the UV, and they channel it into the middle of the hair where there's water, and water's a really good molecule for soaking up UV. So this is a sort of natural sunscreen effort on the part of the plant. And why they think this is important is because at the moment we have sun creams that are made of titanium dioxide, tiny particles which turn UV energy into basically heat and cook your skin. They're wondering whether you could make sun cream out of this. And
so with nanoparticles in it to
well, you could make these
it.
tiny hairs and put the tiny hairs in the sun cream, and the same trick that works for Edelweiss could work for you.
That sounds really cool. Anyway, we are the Naked Scientists, and you're listening to us today. And later we're going to be talking about where did we come from? Where did humans come from? How do we manage to spread across the globe? If you've got any questions for us about science, medicine, technology, and about our topic today, you can email chris@thenakedscientists.com.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
Now, Kat, we've got absolutely loads of emails here. Sarah, interesting email address, purpledancer03, says, is a spider web edible? I presume she means on the part of the spider, not on her part, because she said it's made of protein, therefore can spiders eat it?
Spiders do eat their webs, actually, and sometimes they eat them every day to try and get back in some of the energy they've expended on it. Another interesting use of spider webs, they've got quite a lot of a vitamin called vitamin K in them, which can help your blood to clot. And before the use of gauze, people actually used to put spider webs on wounds.
People are also really interested in spider webs because they're so strong. They're trying to understand how they achieve this amazing chemical feat of being so strong and yet can be made on demand. And I think people are looking towards making this stuff artificially because it would make a great bulletproof vest.
Well, they found the genes, spidroin 1 and 2, and you can synthesise these proteins in the lab. So.
But they have to use insect cells to grow it, don't they? Because the insect cells do some chemical modification.
Yeah.
And because insects are more closely related to spiders, and that's why you need the insect cells, it just means it's more complex and it's difficult to extract the stuff. So they're not at the point where you can scale it up to a whole bulletproof vest yet. But yeah, certainly very interesting.
Interesting. Anyway, we've got a question in from Nikki, who wants to know, after listening to last week's show, she had a question. If our skin is always regenerating, why do we get wrinkles? And I reckon this is the reason, because your skin's regenerating, because you have cells in the top layer of your skin, in the epidermis, that are constantly multiplying to replace the skin that dies. But the bit that holds the structure of your skin is a lower level. It's called the dermis, and that contains a molecule called elastin, which breaks down as you get older, and you also lose the fat in the lower layers of your skin. So actually, although the top layer of your skin is regenerating, it's the bottom layer that's going saggy and makes you wrinkly.
And if you smoke, the chemicals in cigarette smoke also encourage that breakdown to accelerate, which is why people tend to get a lot of wrinkles around their mouth if they smoke. So a good way to anti-age yourself is to stop smoking.
And stop going on sunbeds as well.
Got an interesting question here from Veronica, and she said, my boyfriend Ian and I have been arguing about why it's recommended to put salt on cuts. He thinks that it might have something to do with how salt lowers the boiling point of water. He thinks that the water temperature around a wound is more likely to rise, and the rise in temperature is what kills the bacteria. Seems to be popular advice for dealing with cuts on the inside of your mouth, for example. But what's really happening, and is using salt like this actually a good idea? Well, I think salt, there's no arguing with that. Salt does affect the boiling point of water, but there's no way your skin is going to get hot enough to boil water, even when you have a bit of intense inflammation going on.
It's osmosis, isn't it?
I think so. And the bottom line is that a lot of bacteria, especially the ones that cause problems in the mouth, are bacteria like streptococci and some of the other mouth-dwelling organisms, and they're quite salt-sensitive. When you put a big dose of salt on them, the salt is a bit like putting salt on a slug. It pulls the water out of the bacteria and dehydrates them and can damage them. Other bacteria, though, like Staphylococcus aureus, actually like salt. So if you have a wound on your finger, it might not actually be so good for that, because it'll kill the bugs in there which are not staphs, but it might actually end up with you being colonised entirely by staphs if you put salt on it. So I think it's quite good in very high concentrations. It stops bugs growing, but the likelihood of you getting enough concentration of salt on the wounded area for long enough to kill the bugs is quite unlikely. But it does have a soothing effect, though.
Oh, that's nice. We've got a question for you here, Chris, from Maya, who's 13 years old and absolutely obsessed with our podcast, which is lovely. She wants to know why, if you're standing in a doorway and you push your arms against the door for about 30 to 40 seconds and then step out, your arms go whoop up in the air. What's going on?
Did you do that at school?
Yeah,
we used to do that.
It's cool. You press someone's arms in and then let go and then go, ooh.
They fly up in the air. I think this is to do with the way in which your muscles control their length, because hidden inside each of our muscles is a tiny thing called a muscle spindle. And this is like a miniature muscle which has nerve fibres in it, and those nerve fibres can tell how much the muscle is being stretched or lengthened. And when you put force through a muscle, it's trying to register how hard should I contract? Am I contracting at the right rate? And if the muscle is contracting hard but not going anywhere, then this spindle doesn't stretch, and it keeps sending messages back to the muscle saying, you're not getting any longer, fire harder, work harder. And so when you're pushing up against a wall and your arm isn't going anywhere, it's trying to contract harder and harder to move the wall, which of course doesn't move. Then when you move away from the wall and you switch off the voluntary drive to the muscle spindle is still set to say, I'm too short, I need to be longer, the muscle should be longer than it is. Ooh. So it tells your nervous system automatically, almost like a reflex, to make your arms longer. Hey presto, thanks for that, Ma. It's a good question. It's a really good question.
Excellent. Another quick one. This one's from Nirvana, with unpronounceable surname, who wants to know why opening the car window on a hot day when the car's running feels much cooler than when the car's just at rest. So why is moving air colder?
Oh, this is the wind chill factor. And the answer to this is it's a bit like saying, I'll turn the fan on. Does it make a room colder? No, a fan running does not cool a room. A running fan keeps the room at the same temperature. It just moves more air past you. And air molecules, when they run past you, if you're sweating or something and you're hot, each molecule can take a little bit of heat away from your skin. So the more molecules that pass your skin, the more heat you can lose. So it makes you feel cooler, but it doesn't actually affect the temperature. And that's why driving along fast and nice and fast in your car with the window down, lots of air molecules running over you, cools you down.
And not with your tongue hanging out. Anyway, it's now time to join Ben and Dave for our Kitchen Science. And as usual, they've gone to the pub this week and they've got a hot trick that you can do with a candle.
Hello and welcome to Kitchen Science. Today we're in the Free Press pub in Cambridge and Dave's going to show us a little trick he can do with fire. Here to help us out with the experiment today is Jenny. Hello, Jenny.
Hi.
And obviously I've got Dave Ansell. Hi, Dave.
Hi there.
If you want to try this out at home, Dave, what do you need?
You want a candle, ideally one with a nice long wick, and a lighter or some matches.
Is this safe to do at home?
It's no more dangerous than a candle or matches, so as long as you're safe with those, it should be fine.
So as long as everyone's being careful as they would with a candle at home, what do they need to do?
OK, it's very simple. Just light the candle, wait until it's burning really well, and ideally so you can see a little bit of red ember at the end. Blow it out and then wave your lighted match or lighter somewhere near it and see what happens.
Are we just blowing this out and lighting it again?
Don't actually touch the wick, just try and touch the smoke coming out of it.
OK then, so if you're at home and you want to try this out, grab a candle, light it, let it get burning for a bit so there's a bit of a pool of wax around the bottom, and then quickly blow it out and hold a lighter or a lit match near the wick, but not actually on the wick, and see if anything special happens. We'll come back to you later on in the show.
So that's it. If you want to have a go at this week's Kitchen Science, get a candle and some matches, give it a go, and call in and let us know what happens. Ben and Dave will be back later on to let you know what goes on.
This is The Naked Scientists with Dr. Chris and Dr. Kat, and in 2 ticks we'll be surfing over Everest in a paraglider, courtesy of Meera Senthilingam. She's been to meet Bear Grylls, who was the guy who broke the Guinness Book of World Records record for the highest paragliding flight. That's coming up in a second. And also on the way, the Garden of Eden. Where is it? Where did modern humans come from? When did we first start using fire? And also, where did the English Channel come from? That's all coming up on The Naked Scientists.
Laying the facts bare, The Naked Scientists.
Now, it's always been an ambition of man to be able to fly, but now the new technology and extreme sports have come together and brought this dream a little bit closer, so that adrenaline junkies just like me can rise to even greater challenges than before. And it seems that it's no longer impressive just to have been able to climb Mount Everest. Now the goal is to fly over it. And so we sent Meera Senthilingam to a London Science Museum to find out a bit more.
Imagine what it would feel like to fly. And if you could fly, what would it be like to fly over something like Mount Everest, the tallest mountain in the world? Well, thanks to the new sport of paramotoring, which uses parajets to elevate you into the air and then paragliders to bring you back down, not only are people able to live the dream of personal flight, but 2 Brits have managed to break the world record for the height reached using only a parajet. In May this year, Giles Cardozo and Bear Grylls flew above the summit of Mount Everest and reached a height of 30,000 feet. The challenge was known as Mission Everest and was sponsored by technology company GKN. Now, the equipment they used to accomplish this mission was recently displayed at the Science Museum, London. So I went along to see how it all worked and find out just what it took to break this world record. I spoke to Giles Cardozo, who not only flew up the mountain, but also designed the equipment they actually used to get them up there. So I had to start by asking him just what a parajet actually is.
Well, a parajet is an aircraft that you wear on your back like a rucksack, and you have a paraglider wing, which you attach onto a harness, and using the thrust of this engine on your back with a propeller fitted to it, it blows you into the air, and the wing gives you the lift you need. Together you've got a complete flying machine, and you can fly up to 40 miles an hour, up to thousands of feet. In this case, we flew to 30,000 feet with it.
People do this for social purposes as well, so what kind of heights do they do if they're just doing this for fun?
Really, the highest you go is about 5,000 feet, just sort of above the clouds, so you have a nice view. But 15,000 feet, even that is the maximum altitude you could go to with a normal machine, but people never really go that high.
So what was involved in creating the equipment to take you that extra 15,000 feet?
Well, the most difficult thing really was making an engine that would still breathe where there's no oxygen, or very little oxygen. And at 30,000 feet, there's only a third of the oxygen in the air. An engine needs oxygen to run. That's what gives it its power. So we had to make a system that would drive an enormous amount of air or oxygen into the engine to make it produce enough power to keep us flying.
Well, how did you actually manage that? What kind of detail did you have to pay attention to when designing?
The most important thing was the fuel delivery, which is computer controlled, and the supercharging. The supercharger basically is like a little tiny impeller which whizzes around incredibly fast, and we got it spinning at 3,000 times per second. You can imagine that's rotating very, very quickly, and that would blast enough air into the engine, and now the computer then controlled the fuel delivery, and between the two of them we managed to keep the engine running and propelling us into the air.
When actually doing the flight itself, you're using the engine to propel you, but then you essentially switch it off and use the wings.
Well, yes, once you're up in the air, you've got to keep the finger on the throttle. You've got a little hand control, and you squeeze that hand control, and that keeps the engine revved up, and you keep being blown higher and higher and higher. Now, when you get to the maximum height you want to go, you can switch off your engine, and the wing keeps flying, so you can just glide back down again. So what we did, we flew to 30,000 feet, switched off the engines, and glid all the way back down to our starting point.
And at heights like that, the actual person himself must need extreme protection to protect their own bodies.
Yeah, we had a wind chill factor of about minus 70. We had 3 layers of clothing on board, a whole load of underliners as well, and we had oxygen systems. We'd really pass out under a minute at 30,000 feet if we didn't have oxygen with us. And then a big helmet with about 2 balaclavas on. We had all the kit on to make sure we kept nice and tasty inside our kit.
The amount of power that the actual engine must need to take you up, I mean, it's 100 horsepower. Could you compare that to something just so people can get an idea of just how much power that is?
Yes, I mean, your average family car produces maybe 80 to 100 horsepower, and that's a sort of 4 or 6-seater car. Now, we had the engine equivalent power strapped to our backs, and yet it weighed 10 times less. That was the most difficult bit, was getting an engine to produce nearly 100 horsepower whilst being able to wear it quite happily on your back, and then carrying our fuel with you and everything else. So you realise how light the engine had to be to make it possible to actually make it work at all. If we added up everything, including fuel, all our helmets, electronics, the whole lot, we weighed about an extra 80 kilos, so more than my body weight. on a back. I think I was fitter before I did this trip than I'd ever been in my life, yeah.
And what did it feel like to be at such a height?
Well, I think I dreamt of this moment for such a long time that obviously I was very excited, but also you feel very vulnerable because you're there amongst these huge mountains, miles and miles from anywhere. I think I was scared, but I was also very, very excited. And just an incredible view, really. To top it off, it was just staggering, yeah.
Giles's flying partner was adventure man Bear Grylls, who must have been facing some personal demons in this mission, having broken his back in 3 places in a previous parachuting adventure. I asked him how it felt to be hovering over the tallest peak in the world.
I always thought, God, I wonder if it's going to be really, really terrifying just being suspended in these little strings. But it just felt the most meant-to-be magical, extraordinary, privileged moment. And even though it was minus 40 degrees and you're so dependent on this one little oxygen canister for keeping you alive and you're aware you're at your most vulnerable point, there was something I think we both felt that this was really meant to be and what a privilege. And we'd had screaming winds for days, 100-mile-an-hour winds, massive snows, and we just had this 3-hour window of absolutely still weather all the way up to 30,000 feet. And to get still winds at 30,000 feet is unheard of. You speak to any pilot, you always have at least 80-mile-an-hour tailwinds or headwinds. And it all came together for those 3 hours, of which we did feel the luckiest men alive.
I can't even begin to imagine the physical endurance required to survive at such a height, let alone having to control something that's suspending you in midair. To get you thinking about how high Mount Everest actually is, and therefore how high in the air the duo were flying on their own, I'll leave you with this comparison from Michael Vore, a member of the GKN team.
When you think about it, 30,000 feet is the height of an aircraft flying. So when you go on your holidays and you're flying at that type of feet, you imagine looking out of the window and seeing a guy in a parachute basically flying past you. It's quite a challenge.
Those are absolute nutters. That was Michael Vore, and before him Bear Grylls and Giles Cardozo from the Mission Everest team talking to Mira at the Science Museum. Absolute crazy guys.
Incredible to think that you can fly over Mount Everest. I think they did actually say in one of the newspapers that the guys were more worried when they were asked what's the most dangerous thing, what were you most worried about in this mission, and they said ending up in China. Because I think they didn't have permission to fly into Chinese airspace. It could have been nasty. Anyway, it gives me great pleasure to welcome, he's actually from the University of Wollongong, originally in Australia. He's now back in this country, where he's a professor at Exeter University, and that's Chris Turney. Hi, Chris.
Hi, Chris.
Welcome to The Naked Scientist. If you don't know where Wollongong is, by the way, it's a wonderful little place just down the coast from Sydney, and I went surfing there. So nice beaches, I have to say. So only Australians living there. Wonderful place. Chris, your work has largely been very exciting because you got to do things like date these hobbit people that were discovered a few years back. But probably a lot of people are wondering, where does man come from? And could you possibly set the scene for us, telling us what the timeline is for the sort of evolution of people on Earth and where we all came from?
Yeah, sure, Chris. Essentially, the earliest remains of humans are in Africa, about 2.3 million years ago. And that's a species called Homo habilis, or handyman. Anthropology is remarkably sexist, actually, so it's always man. But anyway, so Homo habilis was the first species of our genus. After that, it all gets a bit hazy. Traditionally, it was always thought that an offshoot of that was Homo erectus, erect man. And the traditional view was that Homo erectus at some point migrated out of Africa and settled across different parts of the world. In Asia, Peking man, Java man down in Indonesia. In Europe, it eventually evolved into Neanderthals. So that was a traditional view, and that's one of the views, and that's called the multi-regional hypothesis, which essentially is that these different species around the world evolved into us, Homo sapiens, with a little bit of romantic liaisons on the edge. I wouldn't say that's the widely accepted view now. The more accepted view is the out of Africa hypothesis, which is that our species, which the earliest evidence around 200,000 years ago, evolved in Africa and then migrated out of Africa somewhere between 50,000 years to 100,000 years ago, and then moved out across the world and essentially displaced all these ancient species of humans.
So why do we think that's the case? Why have we changed our view that rather than people evolving in situ, they actually had to come out of Africa twice, if you like?
I mean, there's always evolution going on around the world all the time, but essentially our species looks like the earliest evidence in Africa and nothing broadly comparable. I mean, I guess really ultimately we'll come to that in a short while, but the Hobbit again is also evidence of out of Africa.
How do we know that date, that magic date, 50,000 years ago, what's the evidence for that?
Well, really, it's constrained, really. We've got evidence of modern humans in Europe around 40,000 years ago, 35 to 40,000 years ago. Really, the sort of one of the linchpins is essentially Australia, actually. There's not a lot of evidence of modern humans between Africa and Australia. There's lots of stone tools, but there's very little modern human remains. There's a little bit in Borneo, but essentially it's in Australia. And Australia opens up all sorts of interesting angles because essentially, even during an ice age, when sea level drops at 120 metres, it's always been an island. So people must have actually built boats to get across in the early stages there 50 to 60,000 years ago.
So people were building boats 50,000 years ago. I mean, that's really something, isn't it?
Well, that's right. I mean, we've got no direct evidence of it. And, of course, the alternative is a pregnant woman on a mat of rubble or a vegetation mat or elephants swimming across with people on them. But I think basically boats are probably the more likely one.
So tell us about the colonisation of Australia, because that in itself is an interesting story, isn't it? Because people didn't know exactly when the first settlers arrived there, I guess until you and your various techniques came along.
Well, it's been an interesting story, actually. If you went back to the 1960s, the earliest ages based on radiocarbon dating were essentially around 10,000 years ago. And over time, gradually it's been pushed back until about 10 years or nearly 20 years ago now, it was about 40,000. But there's a limit to radiocarbon dating, and 40,000 is traditionally quite close to how far back you can detect with that method. And then other methods came along, and they basically started coming up with ages of 50 and 60,000, and there was nothing close to that. So my research interest was really seeing if we could push back radiocarbon dating, and were those ages real artefacts of a method or were real?
If we could just explore that a little bit, Chris, why is carbon dating restricted to those certain dates that you mentioned? Why can't it go on ad infinitum?
Well, it all comes really down to this quirky concept called the half-life, which essentially, after a period of time, half of your radioactive element disappears. And so radioactive carbon, or C14, has a half-life of about 5,500 years. So every 5,500 years, you lose half. And after about 7 or 8 half-lives, you've essentially got very little left. So I guess the thing is, if you took a piece of coal, which is millions of years old, and you added to that carbon 1% of something from your body, modern carbon, you'd come up with an age of 37,000 years if you measured that. That doesn't mean the coal's 37,000 years, it's just how far back it can really date.
So how did you crack that nut?
A combination of things. In Australia, in particular, Southeast Asia, probably across large parts of the world, early archaeological remains, a lot of the artefacts are found associated with charcoal, and charcoal's great. There's lots of it. They burn. It's a product of burning, and in many environments it can survive for quite a long time. Problem is, it soaks up everything in the ground. If you've got smelly feet, you use activated charcoal.
Kat knows all about that.
I'm not going to comment on that one. And it soaks up everything, makes your feet smell very nice. But if it sits in the ground for 40, 50,000 years, it can pick up a lot of contamination. So the method that we used was to clean up the carbon out of the charcoal. And then we had a special vacuum line where we basically heated up the charcoal, burnt off all the contamination and cleaned up the sample for dating.
And what did that show you about Australia?
Well, essentially, when we actually tested it out, intriguingly, some of the early sites became younger, some stayed the same age, but a few crucial ones actually became quite a bit older, and one of them got back to around 52,000 years.
So that says people were knocking around in Australia. They must have had the capacity to get across water 50,000 years ago. But also, what about the climate then? Because obviously Australia is struggling now with not enough rainfall, Murray-Darling rivers down to a trickle because so much is having to be taken out for irrigation. Was it always like that?
No, Australia swings backwards and forwards with aridity all the time. But essentially, this is pretty unusual what's happening at the moment. And we've been doing a lot of work out there trying to reconstruct the climate and trying to get a better handle on what's happened in the past.
What do you think has happened?
Oh, essentially, I think essentially we're in a lot of trouble, unfortunately. We're going to have to start doing something pretty seriously.
But if you look at, say, the timing of the arrival of people, because one of the things that indigenous peoples in Australia have been doing for 40,000 years is burning stuff.
That's right.
So is there any evidence that they have brought about any of the change that you see in Australia?
Well, some people have argued that, yes. We've done a lot of dating and looking at reconstructions of what vegetation was like, and there does seem to be a coincidence between changes in vegetation, at least in northeast Australia, and burning. So some people have argued that actually human arrival, catastrophic collapse of vegetation, and effectively the Australian monsoon collapsed and it dried out. I think other people disagree with that view. So there's an interesting debate going on at the moment.
And if we could just turn finally to the Hobbit story, which was kind of really exciting a few years ago, how do these little people fit into this whole picture of the colonisation of Australia and what else is going on around the world at the same time.
Oh, that was great fun. That really was. We were basically interested in trying to work out when Homo erectus died out across Indonesia. And one of the early sites that we were interested in was led by a colleague, Mike Morwood, at University of Wollongong. And Mike was interested in the island of Flores, and working with Indonesian colleagues, went back to one of the key sites that had been excavated before, and there'd been burials found in the surface and lots of stone tools. And essentially, when they were digging down there looking for Homo erectus, they came across an entirely new species of human, Homo florenziensis.
And so there's been various arguments about whether it really is genuinely a new species or not. I've heard people say, oh, it's just a pygmy or something like that. How do we know that it is genuinely a new species, an offshoot?
Well, there's been quite a lot of evidence now presented with the shape of the skull, the actual shape of a whole skeleton, actually, the shoulder blades, the pelvis, the feet, the wrist bones more recently, and the brain size as well. Typically, if you look at the history of science as well, whenever a new species of human is discovered, there's usually some question about whether it's a diseased individual. When the first Neanderthal was found, someone claimed it was a giant bear. Another person was a Mongolian Cossack, got lost chasing Napoleon back from Moscow in 1814. Another one said it was a child who suffered from rickets, got bashed over the head, and then struggled on through life with arthritis. So it's par for the course, really.
But just looking very briefly at the timeline, Chris, how many years were the Hobbit people around on Earth?
Well, some of their traits are remarkably ancient, possibly 2 million years or so. They certainly arrived on Flores by about 1 million years ago, and the most recent evidence we've got is 13,000. But there's some tantalising stories from the locals, Ibu Gogo, the ancestor who eats everything, and the locals insist that they arrived in the island just before the Dutch turned up, just a couple of hundred years ago. So, mind-blowingly, there might have been another species of human on the island.
Thank you very much, Chris Turney. He's from the University of Exeter. He's here in the studio. If you'd like to ask him any questions on The Naked Scientist with Dr. Chris and Dr. Kat, you can email chris@thenakedscientist.com.
The Naked Scientists. For more information, get online at nakedscientists.com.
It's The Naked Scientists with Dr. Chris and Dr. Kat. We're talking about mankind's origins this week, and we're also doing a kitchen science experiment where you light a candle, wait till the wick is glowing red, you blow it out, and then you bring a lighter or a match very close to the wick but not touching it and see what happens. We've heard from Catherine. She is from Ashwell. She's definitely on the right lines. And also Keith in Watford's got in touch and he's on the right lines too. Tell us what happens. Chris@thenakedscientist.com.
And talking of fire, we're now going to speak to Dr. Anne Skinner, who's from Williams College in Massachusetts. Good evening, Anne.
Hello.
Hello. Now, I understand that you've been studying how humans have used fire in history. So can you put it in a bit of context? How far back did we previously think humans have been using fire?
Prior to the work that I did a few years ago, the earliest dates for fire were about 300,000 years ago. That is controlled use of fire by human beings.
So we're talking about campfires here, basically.
Yes.
And then, so what have you done now?
So what I did, about in the 1980s, some bones were found in Swartkrans Cave, which is in South Africa, and they had clearly been burnt. The layer in which they were found was dated to about 1.5 million years ago. And the question was, how did these bones get burnt? And could that be evidence that they were burnt as a result of deliberate human activity? So I used a technique called electron spin resonance. We won't have to spend a lot of time on that. To look at the remnants, the remnants of the burning process. I mean, if you burn something long enough, you get soot. But if you don't burn it quite long enough, you have some other organic materials in it. And the actual ones that you find will depend on how hot the fire was.
So will that be the difference between whether it was a campfire or, say, just an accidental bushfire?
Right, because at the time it was not a forested area. If there was an accidental fire, it would be a grass fire, about 300 degrees centigrade maximum. Campfires go easily up to 500, 600 degrees centigrade. So if these bones had been heated well over 300, that would suggest that the fire that had heated them had been deliberately assembled by the people who were also assembling the bones.
So it was basically a barbecue?
Not really. They weren't. There's no sign that they were cooking. This has been billed as the earliest barbecue, or the South Africans call it a braai. But first of all, if you actually cook something to 600 degrees centigrade, it isn't fit to eat anymore.
I don't know. You've obviously not tried my wife's cooking, Anne.
And also, you couldn't have counted on having the fire all the time. That is, probably what happened was that there was a lightning strike, some bushes caught on fire, and they dragged burning wood back to the cave and used it to protect themselves against the leopards, which were around.
So then that would suggest that humans were using fire 1.5 million years ago. I mean, that's quite a dramatic difference from 300,000.
It is. Oh, yes, yes. It's not actually, in some ways, it's not that remarkable if you stop to think that 1.8 million years ago, some of our other ancestors were, as Chris was saying, migrating up into the Caucasus. And I know climate was milder there, but I'm sure they would have appreciated having at least some knowledge of the properties of fire in the wintertime in the Caucasus.
Thank you very much, Anne. It's brilliant to hear your work. Thank you for joining us on The Naked Scientist.
Thank you.
That's Anne Skinner. She's from Williams College in Massachusetts, and evidence there, perhaps, of the first fire on the part of mankind. Now, we were mentioning earlier about people moving all around the Earth, and one big question is, when did Britain become an island in its own right? And for a long time that's been a big question, but some scientists from Imperial College reckon they solved the puzzle earlier this year, and one of them is with us this week, and it's Jenny Collier. Hello, Jenny.
Hi, Chris.
Thank you for joining us on The Naked Scientist. So what do you reckon happened? How did we become the island that we're very proud of having?
Yes, well, it's been something that's been sort of known about from other scientists for some time, particularly people looking at the record of human occupation of Britain. So we've been hearing a lot about very ancient ancestors of ourselves, humans. But humans first came to Britain about 700,000 years, a very famous site at Boxgrove. And basically, during this period, this is the Quaternary, so the ice ages were coming backwards and forwards. And so living in England was a bit marginal, if you like. So ancient man was coming backwards and forwards across into France and back into Britain, basically as the ice came down and retreated. And what the archaeologists have known for some time is that there's a big gap. Basically, the humans were coming backwards and forwards quite happily, and then for some reason, between about 160 and 60,000 years ago, there's no evidence for any humans at all. And what we did in our group at Imperial is we're a group of geologists. We went out and did a marine geophysical study in the English Channel, where we literally measured the water depths, and we found evidence for a catastrophic large volume flood, which we think effectively cut Britain off, and this helps explain why ancient man couldn't get back in.
Two questions then, Jenny. What do you look for on the seabed that tells you there was a flood? So what's the giveaway sort of signature of a flood, and where did that flood come from?
Yeah, so what we do in terms of telling a catastrophic flood from a sort of normal fluvial processes, as you might imagine, if you've got a very high volume, rapid discharge water, you get all sorts of scours and eddies and a sort of whole group of landforms that you can put together which say these can only be formed by a high volume water discharge, and that means it's not a fluvial river. And frankly, it's enormous. I mean, I've been working in a lot of exotic places, and I never expected to find something quite so astonishing.
So a massive flood, about when? 500,000 years ago?
Yes, well, we haven't dated it yet. So from a geological point of view, the only way we could date it, we call it the smoking gun. So basically we've got the bit that's been carved out. That's the bit that we've found. And so we'd need to go and look towards the edge of the shelf to find out where the sediments that had been carved out had been dumped. And we haven't done that yet.
Where do you think this massive flood came from, though? What triggered it?
Well, that's right. So we've got this great big flood channel, and basically it points to the Straits of Dover. And it's been well known, again, mainly from people looking at animals and also plants, that the Straits of Dover was a land bridge that survived throughout these glacial fluctuations. So man was happily trotting backwards and forwards across between England and France across this land bridge, which is just a geological structure. And so we made this hypothesis that the only way to get such a sudden water release would be to have a catastrophic breaching of a rock dam across the Straits of Dover, which would have released us basically a lake that built up in the southern North Sea.
Well, where did that lake come from?
Well, as you imagine, during a sort of glacial period, there's a lot of... We're on the edge of the glaciers, so there's all sorts of meltwater coming from the ice itself. All of the rivers from northwest Europe, so for example the Rhine, that used to go through the North Sea out into the Atlantic, would all get trapped and build up a big lake, which would be dammed behind this Straits of Dover rock ridge.
And that's what cut us off from France and made us a country in our own right. Jenny, thank you very much.
Thank you.
That's Jenny Collier, and she is from Imperial College in London with the evidence for where it was written as an island, whereas before we had this umbilical cord connecting us to Europe.
Wouldn't it be much easier to get to Paris on holiday if we're still connected? Anyway, it's now time to go to Diana O'Carroll for this week's Question of the Week.
Hello and welcome to an unusually energetic Question of the Week on The Naked Scientists. Join me as I venture into the electron cloud.
Hello, my name's Paul Tevendale from Woking. My question concerns the speed of light. If the speed of light is slower in glass than in air, where does the energy come from to speed it up as it exits the glass into air? And why does this not violate the law of conservation of energy?
The law of conservation of energy states that energy cannot be created or destroyed. It can only be changed from one form to another. As light is made up of discrete waves called photons, you'd assume some extra energy would be necessary to change their velocity.
I am Professor John Rarity. My speciality is in quantum optics. That's the quantum nature of light. In answer to the question as to why the speed of light is slower in glass and where the energy is stored in vacuum and in air to a greater extent, light is not really interacting with the medium it is in. It's oscillating very fast like a very high-frequency radio wave and traveling at its standard speed, the speed of light as we know it. When it enters the glass contains lots and lots of atoms, and around the atoms are electron clouds. Now, the light, when it's in a transparent medium, it can't excite the electrons. It isn't absorbed, but the electrons do like to try and follow the oscillations of the field. As the electrons are trying to follow the oscillations of the field, it means that some of the energy of the light is stored in those electrons, and that whole process, in fact, slows the whole light field down. So the light in the glass is a combination of the electromagnetic wave and the polarization, as it's called, of the electrons, which are traveling together through the glass. And this oscillation of the electrons actually gives a rise to this dielectric constant and refractive index. And of course, the refractive index is the ratio by which the light is slowed as it travels through the solid material. When the light reaches the end of the solid material, it goes back into air or vacuum, and there are no more electrons. So the energy that's been stored in the electrons is transferred back into the light field, and it speeds up again.
The problem with light particles, or photons, is that they have no mass as we understand it. It is better to understand them as carriers of weightless energy, so it is not the case that a photon is given energy when it escapes glass, more that it no longer has to share its energy with the electrons inside the glass. It's a bit like when Dr. Chris walks from a full room into an empty one. All of those admirers basking in his glow will slow him down a bit, but as soon as he leaves, he's back on his purposeful march. What else can photons do? Well, on a future Question of the Week, we'll be looking at this.
Hi, my name is Pete Chirakis. I'm from Minneapolis, Minnesota. And I was out in the back one day, and I was wondering if the sun is shining on the moon late at night, and it's a full moon, and the light's being reflected off the moon onto the plants at nighttime. Do they photosynthesize the light? And if they do, can they survive only on that reflected light, or do they need direct sunlight?
And then I'll be finding out what the worst kind of loud noise is.
Hi, this is Jim. I'm in Virginia in USA, and I have a question about loud noises and the damage they might do to hearing. I'd heard that tools like hammers that make short, loud noises are supposed to be more damaging to hearing than something that makes a long, continuous noise, and I just kind of like to get some confirmation on that.
So take a look at our forum or drop an answer to me at questionoftheweek@thenakedscientist.com. That's all for this week's Question of the Week. Until next time.
Thanks, Diana. And this question did get quite a few of you thinking, so thanks for all your answers. We had Esme, who suggested that there's no change in energy as the photons enter and leave the glass, just change in the local speed limit, c, the speed of light. And because no mass is involved, conservation's energy is maintained. An anonymous Australian, maybe not wanting to admitting to be a physicist, said the light makes the matter in glass emit its own light, which then interferes with the original light, causing a delay. And Giotti said that some of the kinetic energy associated with light gets transformed into thermal energy within the glass, and this loss of kinetic energy reduces the speed of which light was travelling. So, lots of you had an answer for that question, but what about next week? Do you think plants can photosynthesise with moonlight? Do email questionoftheweek@thenakedscientist.com with your answers.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
And now it's time to find out what happened in our kitchen science. So earlier on, Ben and Dave asked you to light a candle, give it a minute, and get the ember burning at the wick, and then blow it out and put a lit match near it. And we've got Catherine on the line who's done this. Hello, Catherine.
Hello.
Hello. What did you find?
The candle relit.
It relit?
Yeah.
Without you even touching the wick?
Yeah.
That's pretty cool. Right, let's find out if that's what's meant to happen and go back to the pub.
Stay on the line, Catherine. We'll find out if you're right. Let's go back to Ben.
Hello again, welcome back to Kitchen Science. I'm still in the Free Press pub in Cambridge with Jenny and Dave. And we've got a candle here. We haven't lit it yet, but we're going to try this little experiment that Dave's got lined up. So, Jenny, would you mind lighting our candle for us?
OK, there you go.
You want to wait for a while. What you're really looking for is the kind of red glowing ember on the end of the wick, because that really helps.
So is it good to get a candle with a long wick, or will a short one do?
The longer the wick, the better, it seems, yes.
OK, then, Jenny, can you see an ember on the end of there yet?
It's getting there, yes.
OK, Dave, this looks almost ready to me. What's the next thing we need to do at home?
OK, so if Jenny blows a candle out, I'll be ready with a lighter and then wave it around the candle and see what happens.
OK, Jenny, what do you expect would happen if Dave just waves a lighter around the candle but not actually touches the wick?
I wouldn't have thought that the lighter would start up again, but it might just surprise me.
OK, then, Dave, are you ready with your lighter?
I am.
And Jenny, are you ready to blow it out?
I am, yep.
On Dave's count of 3, could you blow the candle out, please?
1, 2, 3.
It's relit itself without the flame from the lighter touching the wick.
So there was actually a gap between the flame from the lighter and the wick after you've blown it out, and somehow the flame managed to jump across. Can we do that again, Dave?
With any luck, yes.
OK, once again, on Dave's count of 3.
1, 2, 3.
Very clever. Yeah, it jumped. There was probably about half a centimetre distance between the lighter flame and the actual candle wick, and the flame jumped across.
So what's actually happening here?
Well, first of all, you've got to understand how a candle works in the first place. The candle's not burning the wick itself, it's burning the wax inside the candle. But this doesn't burn normally, so you've actually got to heat this up really quite hot for it to burn. It won't burn as a liquid, it's got to vaporise and turn into a gas to burn. That way it has lots of surface area and the oxygen can get at it, react and give off energy and burn.
Because, of course, if wax itself burnt, then you wouldn't be able to use candles because they'd just be a pillar of fire.
Yeah, they'd turn into a great big fireball. In fact, if you heat up a candle hot enough, it will all burn at once and you get flames about 8 to 10 inches long. I wouldn't suggest you doing this at home.
So it doesn't actually burn the wick, it burns the candle vapour coming through and around the wick. So what's the wick actually doing?
Well, first of all, the wick is moving molten wax from in the base of the candle up through the wick by capillary action. It's very similar to if you get some kitchen roll and put it in water, the liquid will move up through the kitchen roll, and so the wax gets drawn up by capillary action through the wick. Then the wick's got lots of surface area and it's really quite hot, so the wax will then evaporate, will boil and turn into a vapour on the wick, and then come out of the vapour, and it's that vapour which burns.
So all the different strands inside the wick mean that it's got a lot of surface area for its size. And that's really hot, so the wax can boil and vaporise, and that's what burns.
Yes, so you've got this wax vapour burning in the oxygen of the air, and that's giving off the heat. When you blow it out, you take away the heat so it's not hot enough to actually burn, but there's still quite a lot of wax vapour about. And that's what you're lighting with a lighter, and it jumps through this wax vapour, relighting the candle.
So it's actually just a cloud of wax vapour that you're lighting, which is why you don't need to touch the wick with the lighter flame.
Exactly, yes.
Well, what do you think of that, Jenny?
Very clever. It's not something you think of when you're just going to go and light a candle when the electricity's gone out or anything else. It's very clever.
Fantastic. Well, that's all we have for Kitchen Science this week. We'll be back with more next time.
Oh, that's great. And now we've got Catherine again. So, Catherine, hello.
Hello.
You got that right. Was it what you expected?
Yeah, sort of. But I wasn't quite sure what happened, but I thought something heated up and...
Yeah, it's the wax boiling off, so that's what you're lighting. So well done on that, and keep tuning to the Naked Scientists.
Yeah, okay.
Great to have you with us, Catherine. Thanks very much. The other people who Catherine pipped to the post on that were Keith in Watford, Gemma from Spalding, and also John from Colchester, who also wants to ask you a question, Chris. Hi, John.
Hello there,
What's your
Chris.
question for Chris Turney?
If man and ape had a common ancestor in Rhodesia thousands of years ago, what additional input came into the human line to evolve the white European, the Chinese, the Indian, and also why are there apes in the zoo? I.e., why did one ape decide, I fancy being a man, and another genus of ape said, I'm quite happy being an ape. And 20,000 or 100 million years later, we still have apes.
Well, John, that's a great question, actually. Essentially, we're all apes, and I wish it had been as easy as
some more than others.
Well, we all know a few throwbacks. But essentially, all of them have evolved separately. I mean, we separated from chimpanzees somewhere around 5 million years ago or so, and we've all evolved in our own different ways since then. It's quite an interesting question that, why are some in the zoo and others aren't? I guess essentially it doesn't say much about us as a species. And if we found a hobbit today, would we put that in the zoo? It would be quite an interesting one. But it's not just evolution by anatomy as well. I mean, there's recent evidence showing that some groups of chimpanzees in Africa have actually developed the use of stone tools several thousand years ago. So have a stone tool age for chimps. Fascinating stuff.
So thank you very much, John, for asking. That's a great question. Nice to have you on the programme. Cheers, John.
See if we can do this one really quickly. I had an email from Matthew von der Aar, who wants to know, when Native Americans came over from across the Bering Land Bridge, why did they come? Was there something really wrong with Pleistocene northeast Siberia?
Around 13,000 years ago, but very quickly, possibly a lot earlier.
But was there some climate was horrible or something like that?
No, I think it was just a migration of people around the Pacific at the time. It's fascinating. Not too sure exactly why.
Thank you, Chris. Right, well, I've got one quick thing I want to read out, which is from Oscar Yildirim, who I was having a debate with him earlier this year about why people are white the further north you go. Obviously, in Africa, lots of benefit to having dark skin because it protects you from skin cancer, and as you get further north into Europe, there's no point because it's grim up here and we don't have as much sunshine. Now, I made the case that if you have all this extra blackness in your skin that you don't need, it's a waste of energy, and Oscar points out, very rightly of course, that also if you don't have enough sunlight hitting your skin, then you are more likely to get vitamin D deficient, and that's a very good point, and thank you very much for raising that, Oscar. A bit more vitamin D if you're pale-skinned, which of course we need up here in the frozen wastes of Europe, so thank you very much. Right, well, that's all we've got time for this week, so it remains me to say a big thank you to Chris Turney and Jenny Collier, who came in and helped us this week, also to Anne Skinner, who joined us to talk about First Fire, and our wonderful production team, Ben and Mira. Next week it's our science Q&A show. Any question goes, just send it to me, chris@thenakedscientist.com. Thank you for listening, have a great week and see you next time. Good night.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.